Hello, this is Ziyu Li, and I'm doing the presentation on electrostatic discharge device protection. This is the agenda of this presentation. ESD, electrostatic discharge, is a major consideration in the design and manufacture of ICs because it can have serious detrimental effects on all semiconductor on ICs and the system that contains them. Today, as the scaling down of the CMOS process proceeds, the chip size of integrated circuits is continuously being miniaturized and the operation speed of ICs is increasing. Smaller size of the ICs also reduces the power consumption. Because of the trends, ESD problems are increasing in the electronic industry. Static charge is a non-balanced electrical charge at rest. Typically, it is created by the insulator surface rubbing together or pulling apart. One surface gains electrons while the other one loses them. This resulted in an unbalanced electrical condition known as static charge. When a static charge moves from one surface to another, it becomes ESD. ESD is sudden flow of static electricity between two electrical charged objects for a very short duration of time. The most spectacular form of ESD is the spark, and lightning is the most common example of ESD in the nature. It can be called as miniature lightning bolts. ESD can occur only when the voltage differential between the two surfaces is sufficiently high to break down the dielectric strength of the medium spreading the two surfaces. The movement of a static charge creates a current that damages or destroys gate oxide, metallization, and junctions. ESD damage to electric components can lead to catastrophic failure and latent defect. Catastrophic failure causes a failure in an ESD-sensitive item that is permanent. The ESD event may have caused a metal melt, junction breakdown, or oxide failure. Normal inspection is able to detect the catastrophic failure before shipment, so it could be seen as the least costly type of ESD damage. A latent defect can occur when an ESD-sensitive item is exposed to an ESD event and it partially degraded. It may continue to perform its intended function, so it might not be detected by the normal inspection. However, intermittent or permanent failures may occur at a later time, and these failures are always costly and sometimes severely impact the reputation of a company's product. In general, unprotected MOS devices can only handle 100 volts of ESD. The average person can feel ESD events that exceed 3000, which is 30 times the damage level of an unprotected modern integrated circuit. As the amount of charge generated by the average human or assembly machine can reach voltage in the range of the thousands of volts, ESD protection are vital to the long-term reliability of ICs. ESD can affect production yields, manufacturing cost, product quality, product reliability, and profitability. Industry experts have estimated that the average product loss due to static is from 8 to 33%. Others estimated that the actual cost of ESD damage to the electronics industry is running into billions of dollars annually. Here is a chart showing failure rates associated with various reliability issues. As you can see, ESD caused more than 10% of all failures of electronic devices. ESD can damage ICs and electronic devices. Standards are developed to enhance the quality and reliability of ICs by ensuring all devices employed have undergone proper ESD design and testing, thereby minimizing the detrimental effects of ESD. Three major stress methods are widely used in the industry today to describe uniform methods for establishing ESD withstand threshold. They are Human Body Model (HBM), Charged Device Model (CDM), and IEC System Level ESD. IEC is the name of International Electrotechnical Commission. The human body model is a component-level stress developed to simulate the action of a human body discharging accumulated static charge through the device to ground, and employs a series RC network consisting of a 100 pF capacitor and a 1.5 kilo ohm resistor. The CDM, Charged Device Model, is a components-level stress that simulates charging and discharging events that occur in production equipment and processes. The IEC System Level ESD is a widely accepted European standard which defines an ESD event that is meant to be tested on actual end equipment to simulate a charged person or object discharging into electronic systems. ESD damage occurs when people, robotic arms, and other equipment in manufacturing environments handle devices. It also comes from the charge storage of the package itself. ESD is a subset of EOS. IC failures due to ESD can be reduced by two ways. The first one, ensure the proper handling and grounding of personnel and equipment during the manufacture, transportation, and application of the ICs. The second one, add protection circuits to the pins of a packaged IC to divert high currents away from the internal circuitry and climb high voltages during all ESD stress events. The typical ESD protection method is using an ESD diode in the input or output pad of ICs. In the figure of the schematic, DVDD and DGND are two ESD diodes connected to VDD and GND pads to protect the inner circuit at the input pad of the IC. The right figure is the equivalent circuit during normal operation. If an ESD event with a positive polarity occurs at the signal pad, the DVDD located between the VDD and the signal pad will shunt the ESD current in order to protect the inner circuit. The ESD survival level or the ESD protection level of DVDD and DGND can be determined by the area of the PN junction of the diodes. Accordingly, to improve the ESD protection level, which is the highest voltage that the circuit can accept of an entire RC, the area of the PN junction and the size of the diodes need to be increased. However, if the area of the PN junction of the diodes increases, the parasitic capacitance, CVDD and CGND, induced by the ESD diodes are also increased, and the bandwidth of the input RF signal is restricted by the parasitic components. In general, to minimize the degradation induced by the ESD protection devices while the ESD protection level are maintained, the series connection is often adapted. Theoretically, the size of diodes are the same. The capacitance of series diodes are half of the single ones with the same level of ESD protection. Unlike the theoretical assumption, The ESD survival levels of a single diode and of a series diode are different from each other because of the thermal distribution. The p-n junction of the diodes can be regarded as the thermal source during ESD events. In general, the thermal conductivity of the material of the semiconductor is degraded as the temperature increases. From the figure, it is clearly that the peak temperature of the series diodes is higher than single ones by the thermal interactions. So in reality, level of ESD protection of series diodes is lower than single diodes, but with smaller equivalent parasitic capacitance. Here's a new method from one paper to improve the typical method of ESD protection using the cell-based diodes instead of normal diodes. The cell-based ESD diode is designed using a distributed layout technique in order to minimize the thermal interaction between the adjacent p-n junctions and hence to reduce the peak temperature during ESD events. Here is the figures of the single cell-based diodes and the cascade structure of the cell-based diodes. Here are the figures of the layout of typical diodes and the cell-based diodes. There are 8 diode cells in one cell-based diode using the distributed layout technique shown in the right figure. Compared with these 2 types of diodes, each small diode inside the cell-based diode is much smaller than the typical single diode, but the size of the whole diode cell is larger than the single one. The research team used the ESD model of a 150 pF capacitor and a 330 ohm resistor to measure the ESD survival level to test the feasibility of the method of using cell-based series diodes. From the figures, the average voltage of using cell-based diodes are larger than using the normal diodes, which means that using cell-based diodes can protect the devices better than using normal diodes. And the experiment also showed that the performance of series cell-based diodes is better than that of the single ones, which is opposite to the typical method, because of the reduction of the normal interaction. The other figure indicated that the required p-n junction area of the cell-based diode is less than the area of typical ones. ESD protection design must handle complex multiple coupling effects involving transient, electron, thermal, process, device, circuit, and layout aspects. Several key challenges must be carefully considered in ESD protection design. First, the decades-long traditional ESD protection solutions rely solely on conduction via N-silicon p-n junctions in various formats. Consequently, the inherent ESD-induced parasitic effects, including parasitic capacitance, noise, and leakage, will affect the IC performance. Second, the in-silicon ESD protection structures, often large, in both core silicon devices and metal interconnections. To ensure robust ESD protection, not only consume significant silicon area, but also cause difficulty in IC layout. The trend of IC nowadays is scaling down, so the in-silicon ESD protection is not adapted to the development of the industry, and a new on-chip ESD protection method is needed. On-chip ESD protection depends on both the ESD protection structures and the ESD metal interconnects on a chip. Often, though an ESD protection structure may be designed to handle strong ESD surge, the metal interconnects may be the weak point, resulting in low ESD protection level for the whole chip. In addition, excessive ESD metal interconnect required for robust ESD protection introduced more parasitic effects. Improvements over traditional AL or CU interconnects will be critical to hold chip ESD protection design. Graphene is a two-dimensional material made of carbon with many unique properties, including high thermal conductivity, which could effectively mitigate the overheating effect in metal interconnects, and high current handling capability, which is very suitable for conducting fast and large current surges like ESD discharging. Graphene is one of the strongest materials known today, with a Young's module of around 1 TPa. So it is the potential replacement for metal interconnects of ICs. The high current handling capability of graphene ribbon makes it not only more suitable for robust ESD protection, but also possible for using much less interconnect coverage, and it can create much lower parasitic capacitance in small layout area, which are critical to advanced ICs nowadays. For ESD protection, a high thermal conductivity means much reduced overheating under ESD stressing. In addition, graphene film may be used as a heat spreader around an ESD protection structure to rapidly spread out the ESD-induced heat, thereby greatly reducing the possibility of ESD-induced hotspot effect, which is the root cause for ESD thermal failure because silicon is poor in thermal conduction. The outstanding mechanical strength also makes a graphene ribbon a perfect candidate for interconnect, which is often a weak point for on-chip ESD protection. This figure illustrates a conceptual on-chip ESD protection scenario using graphene ribbon interconnects. GR wires connect ESD structure with pads. During ESD events, large ESD transients will discharge through GR interconnects and the ESD devices. Hence, the GR interconnects must survive the ESD surge. The size of GR wires is important. If a GR wire is too short and narrow, it may not catch material defects because the current graphene film growth process is far from mature. So it is possible to design a long and wide GR, and the GR wires should have dimensions suitable for real-world ICs to ensure the useful results. There are some problems during the experiments of the GR interconnect. The GR sample quality may not be well controlled due to the current graphene growth processes, especially for volume production of large-sized graphene films. GR test results may be very sensitive to test conditions. Therefore, one should focus on statistical analysis instead of single sample. The trend of designing and manufacturing ICs is scaling down. As an important part of the industry, ESD protection should be developed to follow the trend. The typical method of ESD protection is using the ESD diodes to shunt the ESD current if necessary to protect the inner circuit, but this method needs a large area of diodes to increase the level of ESD protection, which is not suitable for today. The improvement of use in cell-based diodes is a good idea to increase the ESD protection level by reducing the thermal interactions between diodes. The performance of this method is better than that of the typical one, and the required area of the diode is also smaller. Cell-based diode is a good improvement of on-chip ESD protection design, but with the development of ICs, traditional methods cannot meet people's requirements, and new materials and new designs became the critical part of the IC industry. Graphene is a good potential replacement for metal interconnects, but the technology of how to use graphene is not good enough to create the graphene film with the same standard. More researches and experiments are necessary for this potential candidates of future ESD protection. Thank you very much for listening.